Okay, hi folks, my name is Andrew Margenot. I'm a relatively new addition to the Department of Crop Sciences. I'm about 4 years in, and so my background is soil science. That's what I do. I'm not an agronomist, that's the disclaimer. I think about what lies beneath in a more mechanistic way, let's say. So I come to you to share some ongoing work to update the Illinois Agronomy Handbook, and specifically the Handbook Chapter 8, I know you all know it by heart, which is on pH, phosphorus, and potassium. So the specific update that we have in mind here, has to do with the concept of subsoil pea supply power. There's a lot of synonyms for this, but the basic concept is that if you go beneath the top 6 inches, there's going to be soil that will provision phosphorus to crops. So this is not unlike the N-credit concept, insofar as that you are able to credit a non-fertilizer source in that season towards crop uptake. So there's a lot of issues. Some are surmountable, some are maybe trickier to deal with in order to update this concept. The concept itself is from 1905, and there's been a long period of time since we've found some new things that might mandate site-specific tailoring of the concept to make it useful. So this is all abstract. Let's talk about some details. First, thanks to the funders of this work, NREC especially, for driving a lot of the research. So as a bit of background, I think a lot of you know this concept of the build and maintain paradigm. It's how we currently, in our state and in much of the I states, the Corn Belt, we think about adding nutrients for crop production. So the easy part is the maintenance, simply what are you taking off as grain or as silage, and then you've got to put on that amount in terms of NPK. Pretty simple, it's a mass balance. Then we've got the build versus the drawdown, and the concept of build is that there is a critical value, and that critical value is a number on your soil test. So whether it's Bray or Melick, it's going to be something like 30 pounds per acre equivalent, and you want to build up to that critical value. So these values, they differ by the soil test type and by the stage and by the crop, but the whole idea is that this is the value that you're going to build to. So you'll add more than crop removal to get to the build critical value. Okay, so the reason why I tell you all that is that this is all background here, but the critical values, they're a lot messier than what we think they might be. So you see these very neat, smooth curves typically. In reality, when you see how the sausage gets made, it's not as pretty, and it looks something like this. So if you stare at this, you'll realize that the optimum, thus the critical value that you're seeing here for O, is right around here, but it's very much an average. It's in the middle of a cluster of points, which means that for your specific field, you might be right on the critical value, but in other fields, it may not be sufficient. In some contexts, it might be too much. So I show this to you just to give you a feel for that these critical values are estimates. They're based on the probability of a yield response on a statewide average. So think about that, because obviously soil types are quite different across our state. Because of this, there's a need to finesse what the critical value is. So one approach to finessing this was the subsoil pea supply power concept. And the idea was that depending on where you sit in our states, you may have different capabilities of your subsoil, and that again is beneath the top 6 inches, the ability of the subsoil to supply additional phosphorus beyond what you've put on. And that can help you interpret the critical value. So there's 3 major zones that were postulated back in 1905, 1910, and this is what it looks like today. This is from the handbook directly, Chapter 8. So we are sitting in the high region, and this has to do with the geology of the state and really the loess, how much loess and what was the age of the loess. Also drainage, and these 3 things interact to determine your soil pea sub-supply region. Okay, so here's an example of why this matters. If you look at the handbook as well, here's that conceptualized critical value. Note how smooth those lines are. You just saw a good example of how they're a lot messier. But the whole idea is that you want to build your soil test value to be, in this case, from 40 to 50 pounds per acre. But that range, which differs by 25%, 40 to 50, that range is determined by where you sit in terms of regions of subsoil pea supply power. So in other words, the same number might put you at that okay value if you're in the high region, but it will not be sufficient if you're in the low region. So how people interpret their soil test has been in part determined by this concept, and the magnitude again is about 25%. So let's talk about where this concept came from to understand how it might be improved for today. The concept itself is from a bunch of papers from the U of I from the 1960s, but itself was conceptualized by Cyril Hopkins, one of the first soil scientists at the U of I, 1905 to 1910. So here's what you just saw from the handbook, and as I've mentioned, the concept of having more subsoil supply power. You have more of that if you have basically younger loess, thicker loess, and better drainage. So the loess is the bank accounts, both how much is stocked up there and what type it is. And then the drainage matters because if you've got very poorly drained soils, if they're not tile drained, then your roots can't tap into it. So you kind of need drainage as part of the equation. Now, think about as we tile drain lots of our regions, this concept is already a little bit outdated. So again, from 1905, yeah, there was clay tile, but not at the scale that we see today. So the figures on the right are the actual hand-drawn figures that they were making in the early 1900s. And you can kind of make out how you see there's two kinds of loess. The Wisconsinian is the younger event. The Illinoisan was the older event. So the Illinoisan loess that tends to be more common in this region right here, and you can make it out on the east side of the map, well, that tracks with the low to medium supply power. And the more younger Wisconsinian loess, what we're sitting on right now in the west side of the state, it's younger, it has retained more of its phosphorus. Just like people's soils get older and they lose their fertility. So then we also have the thickness, and that's what you see here. Basically, I put in numbers here, the loess out here is 4 to 5 feet deep, 3 to 4 feet deep in this medium zone where Champaign is. And note that the low region can be even thicker than out west, up to 7 feet deep. But it's a lot older substrate, so it's lost its phosphorus. So there's three things going on here. The third thing would be, here's a more updated map of the loess thickness, what you're seeing here in the 1960s. They updated it about 2 years ago, but it's the same basic concept. It gets real deep if you're in the western part by the Bluff region of the state. Let's talk about the drainage. The drainage is one reason why we may need to update this concept, because the whole idea is that you may have a lot of phosphorus stocked up in the subsoil down to 5 feet in the loess, but if you're poorly drained, those roots can't access it. But as we've begun to tile drain, especially in those low regions of the eastern side, so for example in Champaign, it's great soil, the Drummer Flanagan type, but it sure is wet. And you really cannot produce good corn in most years if you don't drain a lot of those low spots. This drainage, this right here, is a map of the drainage class. And so think of blue as less well drained, green to yellow is better drained. And so this is also the low supply region, in part not because of the lack of phosphorus banked up, but because of the poor drainage. So with tile drainage, the low region may actually become a medium to a high region. So a reason to think that this map needs to be updated. So let's talk about loess itself and the chemistry. This sets up for the final point. Loess, by the way, is that yellow grayish stuff. Here's a good example from down south by Glen Carbon. Loess is basically a silt, windblown substrate. So we had glaciers here. The glaciers melted. It was all tundra. And then the winds brought in from Canada fine talcum powder type consistency stuff. And this stuff is the inheritance that was bestowed upon the land by the glaciers. It's rich in nutrients, including phosphorus. And the main mineral of phosphorus is apatite. A lot of puns can be made about being hungry, etc. But apatite is spelled A-P-A-T-I-T-E. Apatite is calcium phosphates, which, by the way, was the first form of fertilizer as rock phosphate. Calcium phosphate, same thing. So calcium phosphates don't dissolve very easily. They do dissolve in low pH, like the rhizosphere of crop roots. So the whole idea of loess being a bank, a slow burn bank account for your crops, is that if the roots can get down into that subsoil where there's loess, it can chip into the uptake of phosphorus. Very slowly, though, because it's not very soluble calcium phosphates. Here's an example of the magnitude. This is data up from Monmouth, where we looked at at 4 different depths, so every 6 inches. So this is in centimeters, in metric. So 0 to 6 inches, 6 to 12 inches, and then 1 to 2 feet and 2 to 3 feet. So down to 3 feet. And the apatite that we have interest in, which was, again, inherited, it's from the loess, is in purple. As we go deeper, the importance of the loess contribution to the phosphorus supply increases proportional to the other sources. So your soil test P would be here in blue. Note that there's a lot less soil test P compared to the loess contribution. Of course, more of the little blue stuff is immediately crop available. So this idea of subsoil supply power, as I mentioned, is from an older time. This is Cyril Hopkins shown here, one of my favorite books written in 1908, The Farm That Won't Wear Out. And his interest was in how can we manage fertility in a way where inputs, or rather cost of inputs, are minimized. And so if you look at this book, he began the task of trying to quantify this natural capital, what's the bank account of phosphorus. And he already points out what we now think of as the subsoil supply regions. He was noting in 1905 or 1908, that there was more phosphorus. So we've got 1,200 pounds per acre in the northern central region with darker soils. And then if we get into the south, lighter soils, we get a little bit less, 840 pounds per acre. These values are pretty darn accurate. We've done measurements at similar sites, and he's off about 5%. So that's 1908 with a lot less fancy toys than what we have now in the lab, and they figured it out more or less. So what we're doing right now with NREC support is that we are trying to quantify the site-specific, or let's say within county level, P bank account. I'm pausing there because subsoil supply implies uptake. We're not going to measure uptake yet, but simply what is stored. The map that you saw from the handbook in those different shades of green is very coarsely drawn. We want to have higher resolution, sub-county level. So for this, we have a great discovery, and Alan Parrish has been instrumental to making this happen. We have an archive of soils, here's but a snippet of it, that date back to, at the earliest, 1861. So these are the soils that were taken as part of the soil survey in our state that even predates the existence of NRCS. Because they go back to 1861, most are 1900-something, we can resample those positions and learn how the parent phosphorus bank account has changed. But also, more importantly, we have site-specific measurements. So we can actually get numbers more quantitatively on what that map you saw looks like. There's going to be a lot more pockets. If you think about the map of the loess thickness from 2019, it's more variegated. It's more detailed. So we anticipate that any map of subsoil P bank accounts stocks will be more complicated or complex. Okay, so what we're doing then is to quantify over in 4,000 different sites just how much phosphorus lies down to 3-foot depth. And this is a map that shows you all of the samples that we have to 3 feet across the state. They were taken from as early as 1901 for the soil survey all the way through present day. And we've got some outliers that go back to 1861. Here's what they look like, pretty old, a gold mine that we're going to use for this work. Okay, so I've got a couple of minutes, and I want to touch on why this stuff matters beyond just informing the critical soil test value, also work supported by the Farm Bureau and by NREC. So this brings us to the topic of legacy P. So one reason why those maps of the subsoil P supply power may not be as accurate today is tile drainage. The other reason is that we have banked up phosphorus, sometimes without meaning to, from past applications. And this concept is known as legacy phosphorus. Basically, the idea that you have put on more than what the crop took up. And a common example of this is rock phosphate. There were very high application rates being made up to 1 ton per acre back in the day. Rock phosphate is the same as what loess has, calcium phosphates. It's still going to be there after millennia if it hasn't dissolved. This matters because the bank account might have been increased through inputs in the past. And this also matters then, so that's important for, say, drawdown. The second reason why this concept of what we've built up matters is that it might be a reason to reconsider the nutrient loss reduction strategy goals. So NLRS, it's what our state has committed to reduce N and P export to the Mississippi. We've got certain benchmarks. The next one is coming up in a few years. So the reason why this matters is that if we've built up phosphorus in the stream banks or in soils and that is eroding, that is from fertilizer that was put down perhaps 50 years ago. And it's unfair to pinpoint that phosphorus loss on current application rates. So what we're trying to do is to quantify the lag between when P was put on with when it's being lost to the state's waters as a way to inform a more accurate target for the NLRS. So a couple of implications is that, again, we may not have the relevance of those maps you saw in the handbook, but also in terms of water quality targets, we want to make sure that those are fair to farmers and also reflect the reality of how P is being lost. Okay, so here's a final ending comment on the first part of the legacy P lets you do economically viable drawdown. Drawdown means that if you have more than the maintenance on your soil test that you can then if you're above the critical value and you're in the maintenance zone, then you can lessen the inputs and begin to mine down to the critical value if you're above that critical value. And here's a good example from Monmouth. We have a lot of legacy P that's been banked up. So the whole subsupply power concept here is not relevant because of that, because of that buildup, because of that accumulation. And what we did here is that over 36 years, we did this pretty simple trial with corn versus corn soybean with no nitrogen and with nitrogen. This is in kilos per hectare. That's not the point. It was meant to look at, with continued grain export of phosphorus, what's the phosphorus balance? So by balance, we mean you subtract the grain output, the pounds per acre, every year over almost a third of a century, 36 years, and you look at the difference of that with the inputs. So over those 36 years, there's only a one-time application of DAP of 200 pounds per acre. So that's what you're seeing here. And then we're taking off this amount of phosphorus over those 36 years. So a pretty big deficit, a pretty big negative balance. And this seems kind of insane. It's roughly equivalent to having exported almost 2 tons of DAP per acre over 36 years. But if you try to contextualize this negative balance right here, it looks like this part of the phosphorus stocks. So what you're looking at in this graph is the total amount of phosphorus. So this is kilos per hectare, roughly pounds per acre, that are banked up to 3 foot. And if you contextualize the fact that you've taken off roughly 1 ton per acre of P2O5, that's only about maybe 25% of what you have left to go in the soil profile. This is an example of why if you've accumulated phosphorus combined with the rich amount of phosphorus from the loess, it lets you draw down potentially for very long time periods. Okay, so that's a lot, but in a nutshell, that's why the legacy P concept is relevant to the subsoil P supply power. And we're hoping by the end of the next 3 years to update the handbook to account for the drainage impact and the accumulation, i.e. the legacy effect of past applications. Happy to take any questions.